We are going to spend the next 20 minutes or so studying lighting. To do that, we're going to use two different types of equipment here in the theater. The first thing is we have the giant red and blue thing in the center of the theater. This is the world's largest and one of the original Van de Graaff air insulated generators. The machine was actually built originally in the 1930s as a power supply for a piece of equipment that was used for physics experiments. To the left and the right of the Van de Graaff generator, we have the tall towers that have the purple donuts sitting on the top of them. They are called coils, and they're named after their inventor, Nikola Tesla. Both the Van de Graaff generator and the Tesla coils produce voltages that approach and go just over, in some cases, 1 million volts. And we're going to use the sparks that this equipment made to talk a little bit about lighting and electrical safety. Because this equipment is actual high voltage equipment, it's not a movie and it's not a special effect, I can't turn it down. Which means that if you or anyone you brought with you just plain old doesn't like bright flashes and loud noises, or is too young to understand what's going on, we do not recommend this presentation for you. If you have little ones that are stroller age, this is probably not a good place to spend the next 20 minutes of your visit here in the museum. Now, here's the thing. The truth is, it's not really that scary of a presentation. It's not like there's like things jumping out of like the walls and stuff like that. It's just that if anyone here is too young to understand what's going on, it can be a little bit startling. So just keep that in mind. If you do need to leave for any reason, you can do that. And it's an open theater, which means you can even come back in again if you want. Sound good? Yeah. Except for him, everyone's good. Alright, so without further ado, let's start by talking about the Van de Graaff generator. The way this machine works is actually very, very simple. It uses conveyor belts to lift electrical charge from the basement up that wooden column into the red and blue metal domes. It's really that simple. Whenever we say it uses conveyor belts, folks automatically assume that's some sort of a metaphor or an example, but it isn't. You can see the conveyor belts up on the left and right. To make this machine work, wicked simple, as we say in Boston, we spin those conveyor belts at 60 miles an hour. Once they get up to speed, which you can both see and hear, we place electric charge on them. That charge gets lifted up those belts from the basement to the top of the machine until eventually so much built up, it jumps through the air and it makes a spark. Now at this point, why doesn't everybody sit back, relax if you can, and cover your ears? I'd like to introduce all of you to what this machine does. Those are the smallest sparks that you're going to see this big machine make today. They're also the second smallest sparks that you're going to see the theater make. The first smallest spark, believe it or not, is actually these. Now, at first glance, especially given what we just saw, these sparks may not actually look like much, so it might surprise you to learn that they're being produced by around 60,000 volts of electric charge. That is a spark from 60,000 volts. And that is the reason that we don't use 60,000 volts to power our houses. If we did, we'd have that jumping out of every plug in the wall of our house and we couldn't have pets. So we choose a voltage that can't jump into the air and zap our ankles when we're walking by it. 110 volts works just fine to turn on your air conditioner without, making an obstacle course when you get up at 2 o'clock in the morning to use the bathroom. So we wind up measuring voltage, or we wind up talking about voltage as a term of potential energy. The higher the voltage, the more energy electric charges have and the more stuff they can do. For our purposes here in the theater, the higher the voltage, the bigger the spark. The sparks you just saw the Van de Graaff generator make were probably around 650,000 volts or so. They were about 6 feet long. The Van de Graaff generator goes up to about 1 million volts, and in just a second, the Tesla coils will make sparks that are approaching 800,000 volts. The higher the voltage, the bigger the spark. But before we go down that road, there's actually something else I want to talk about for just a second. And to do that, I want to completely change gears and talk about stairs. Raise your hands if you have ever wiped out on a flight of stairs. How many of you guys have fallen down the stairs before? I actually fell down those stairs once, and that's a true story. It turns out that gravity is a force that pulls on objects with mass. We've all heard that before, right? We've all got mass, so we get pulled towards the center of the Earth by gravity. Any surprises there? No, probably not. Question. When you trip on the stairs, what do you see? Stairs, right? Why are the stairs that close to your face? Because you just discovered that gravity is a force that pulls on objects with mass. Now, here's the real question. I should have been a little more articulate when I asked the first one. When you trip on the stairs, do you actually see gravity? No? Why not? It's invisible, right? Gravity is an invisible force. When you bring magnets close together, do you see magnetism hold them together? No. Gravity is invisible, magnetism is invisible, and it turns out electricity, which is a force that pushes and pulls on electric charge, it's invisible too. You can't see electricity. That isn't electricity. So that's the first thing we need to start by talking about what thunder and lightning is the fact that that spark is not electricity. It's being caused by electric charge moving through the air, but it isn't electricity. What it is actually really simple. It's hot air. This balloon is filled with air, right? Well, if we put it in the spark, it really doesn't last very long because that spark is very, very hot. Hot enough to pop a balloon in just a second, which is why I didn't stick my fingers in there. That hot air is making light. That air is heating up, the air is glowing, we're seeing it as light. It's also fluorescing, like inside a fluorescent light bulb. We get light without a whole bunch of heat as well. But the spark's hot enough that it makes the air glow. Everybody close your eyes. Close your eyes. Tell me another effect of electricity traveling through the air. We got heat, we got light. What's the third one? Sound, right? We can hear the buzzing sound, so you can open your eyes again. Light, heat, and sound are effects of electricity traveling through the air. We can't see electricity. But when electric charge moves through the air, it will cause that air to heat up. And we can see it, and we can hear it. We call those effects thunder and lightning. And the higher the voltage, the more pronounced those effects become. Case in point, to my left and my right, on the inside of the wires, we have those large Tesla coils. And as I mentioned just a second ago, they're capable of producing almost 800,000 volts of electricity. Now, if you had to guess, would an 800,000 volt Tesla coil make a bigger or smaller spark than a 60,000 volt Tesla coil? I mean, think about it, right? It's probably not rocket science. Little Tesla coil gives you a little spark, so we would expect that a big Tesla coil is going to give us a big spark. Cover your ears, maybe. By the way, in case you were wondering, that's the reason that we don't need 800,000 volts power. Now, one of the things you may have noticed is that the coil on your left, the coils on your left, because there's two of them, they actually made two different sounds. Did you guys notice that? And the one on your right made a single sound. There's a reason why that happens. It's not your imagination. It actually did happen in real life. And to talk about why that is, what I'd like to do is actually take a look at the Tesla coil on our right. That coil over there will produce sparks that are approximately 6.5 feet long. But what I'd like to do for just a second is take a look at the spark that that coil makes, and then after that, I want to take a look at that spark on video, slowed way, way down. Because I think it's going to surprise you what that video actually looks like. So, everybody cover your ears, and let's take a look at that Tesla coil in real life. So watch it with your eyes, first of all. You guys ready? Alright, now, let's take a look at a video up on the screen to the left and right of that same Tesla coil making a spark. So there's a Tesla coil making a spark, and here comes the video. Did you guys notice anything different between what's up in the video and what you saw with your eyes? Yeah, it's flickering, right? Yeah. When we look at it with our eyes, it looks like a continuous spark. But if we play back a video and you really slow the video down, we notice the coil is flickering. And there's a really simple reason for why this is. That coil is actually making one spark at a time. It doesn't make a continuous spark. It makes one spark, and then another one, and then another one, and then another one. But that coil makes 120 sparks every second. Our eyes can't see 120 flashes, and our ears can't hear 120 pops. So the spark looks and sounds to our ears like one continuous spark. It looks and sounds to our eyes, if you want to think of it that way, as one continuous flash. Does that make sense? Remember, we can't see electricity. We also can't hear it. What we're hearing when we're hearing that Tesla coil is that coil wiggling the air, which is wiggling our eardrums 120 times every single second. When our eardrums get wiggled 120 times per second, it sounds just like this. However, with the coils on our left, they are capable of producing literally as many sparks per second as we want. We can make anywhere from 1 or 2 sparks per second up to several 100,000 sparks per second. The more sparks per second we make, the more our eardrums get wiggled, and the higher the sound we hear with our ears. The result of that is we can go from this to this. Can you guys pick up the difference? Yeah. The higher the note, the more sparks per second, or perhaps vice versa is true. The more sparks per second, the higher the note. And the really cool thing about these Tesla coils is we can actually switch them on and off so fast, they can reproduce almost any musical note you can possibly imagine. We can't see electricity. We can't hear it either. Electricity doesn't have a sound. But if we can control how many times per second that spark wiggles our eardrums, we can control exactly what it sounds like. You also probably noticed the spark probably looked a little bit different too. The spark appears to be brighter with the higher notes. Now, that is actually happening. It's not your imagination. But it's not happening for the reason that most people think. The voltage that's being produced, the potential energy of those charges, is exactly the same for the high notes and the low notes. So why are the sparks for the high notes brighter? Well, it's actually really simple. Every time that coil makes a spark, it has to heat the air up. And when there's less sparks per second, the air has more time to cool off in between. So the spark appears to be dimmer. When you have more sparks per second, the air doesn't have time to cool off, so you heat it even more, and it gets brighter. I can actually show that to you. What I'm going to do is play a piece of music right now. Why doesn't everybody cover their ears? I want to see if you can not only hear the difference between the highs and lows, but also pick it up with your eyes. You guys ready? You sure?
Yeah.
You sure you're ready? Yeah. Try that one more time. Here we go. about to the point of the presentation where I want to take just a couple quick minutes to talk a little bit about lightning safety. The good news is this doesn't actually have to be a really super long conversation. Lightning safety is pretty easy to talk about. Lightning tends to be attracted to things that are tall, things that are metal, and things that are pointy. And there's a reason for that. Lightning is generated in a storm cloud in a very, very similar way to the way that you generate an electric charge in your house when you stuff your feet on your carpet and you attack your cat. It works in exactly the same way. The result is you separate electric charges in two materials and you get a spark that brings the charges back together. In a storm cloud, which usually looks just like this mural up here on the wall, you have a very tall cloud that's a little bit skinnier in the center than it is in the top and the bottom. Now, in that cloud, there's dust, there's hail, there's ice, there's snow. There's all these teeny tiny little things bumping into each other. And you're doing literally the same thing that you do when you rub a sweater on your hair. It separates electric charge. In a storm cloud, those charges tend to separate out into three different areas. We get a lot of positive on the top and a lot of negative in the middle. The bottom of the cloud has a much smaller positive charge. If we're going to get lightning in a storm cloud, chances are it's going to jump from the negative up to the plus, or from the negative to the middle down to the ground. If I could light the ground up on that mural, the ground would have a small plus as well. Here's the deal. You never, ever, ever want to be part of the connection between the plus and the minus for a lightning bolt. Electric charge is going to go from the cloud down to the ground where it can spread out. Now, sometimes the opposite happens. Lightning can originate at the ground and travel up. Much less likely, but it does happen. The bottom line is this. If you are tall, metal, or pointy, you are in exceptional danger of becoming part of that connection. Does that make sense? You don't want to be tall, metal, or pointy during a thunderstorm. If you're all of those things, you're very likely to be struck by lightning. If you're a couple of them, you're more likely to be struck by lightning. If you're none of them, well, you can still get struck by lightning, but it's very, very unlikely. What you want to do during a thunderstorm is go inside of a building. Buildings are always taller, always more metal, and always more pointy than you are when you're inside of them. Lightning Safety 101, go inside. I mean, does that make sense? That's what you want to do. You want to go inside of a building. And here's why. Statistically speaking, your house is never going to get struck by lightning. That almost never happens. What happens far more commonly is lightning hits something near your house, like a tree, like a telephone pole, like a fence, like a flagpole, or like your neighbor's house. And then once that lightning hits something near your house, what can actually happen is a little bit of it can sneak its way through the wires into the wall of your house. Well, if you're sitting on your couch minding your own business, it's fine. It's not like the lightning can kick your door down at 2 o'clock in the morning and looking for you. But if you're attached to the wires of the pipes, the lightning can actually get to you through the wires of the pipes. Does that make sense? Lightning Safety 102. Don't plug yourself in. Go inside of a building and don't physically wire or plumb yourself to the wall of that building. Because that's how the lightning can get to you. If you're not wired or plumbed to the wall, you don't have anything to worry about. If what you're doing isn't physically plugged into the wall, then it's safe. Cell phones, text messages, like Xbox Connect, Nintendo Wii, watching TV, all of those things are fine. Not necessarily for the electronics, but for you. As long as you're not physically connected to the wall, you don't have anything to worry about. For the record, I am not saying it's nice to go home and call your next door neighbor that doesn't have a cordless phone during a thunderstorm. As far as you're concerned, fine. It's the physical connection with the wall you want to stay away from. Now, if you can't get inside of a building during a thunderstorm, where do you go? And you're where?
A car.
A car. Is that true? Yeah? No?
Yeah.
Some of you are shaking your head no, some of you are saying, all right, I'll buy it. Raise your hands if you believe that you're safe in a car during a thunderstorm. Let's take a quick survey. Turn the lights up here. Raise your hands if you believe you're safe in a car during a thunderstorm. All right. Raise your hands if you think just because you're on the balcony, you don't have to raise your hands because I can't see you. Because that's not true either. Raise your hands if you believe you're safe in a car. Do it again. All right. Hands down. Raise your hands if you do not believe that you are safe in a car during a thunderstorm. That was not even close to everybody. All right, third question. Raise your hands if you don't know. How many of you are just not sure? Because that's fair too. All right, hands down. Last question. Raise your hands if you realize it doesn't matter in the slightest what you believe. I mean, not to be mean, but if more people raise your hands to say that you're safe, does that actually make you safe?
No.
Of course it doesn't. Now, if I told you were safe, would that make you feel better?
Yeah.
No? Are you kidding me? I can't actually see you guys up there in the corner, but I can see someone chuckling. I'll be right back. Do you have any way of knowing that I actually know what I'm talking about? I mean, it's creepy as to see, so you don't even really know that I work here, right? I mean, for all you know, I have the real lightning guy tied up in the basement downstairs. You have absolutely no idea. The point being is that you're not going to believe someone that you just met for no reason. You're going to look for evidence. And in science, the way that we get evidence is by doing experiments. So let's end this presentation by doing an experiment. The first thing I need is a car. Now, sometimes in science we use models. A model is an object that takes the place of something else. For example, this is going to be a model of a car. Now, I know it doesn't look like a car, certainly doesn't move like a car, but this cage actually has everything in common with a car that I need to not die during a thunderstorm. This cage is metal on the sides, metal on the top, and metal on the bottom. So are cars, trucks, trains, tanks, airplanes, submarines, trash cans, dumpsters, tin shacks, suits of armor. I ran out of things, but you guys get the idea, right? As long as you're in some sort of vehicle or some sort of thing that is surrounding you with metal on the top, on the sides, and on the bottom, believe it or not, you don't actually have anything to worry about from lightning. And I know that sounds really weird because we're used to metal conducting electricity. But in this case, it's a property of lightning and metal that are going to combine together to keep us safe. When a spark from this Van de Graaff generator, or the Tesla coils, or a real lightning bolt hits this cage, it creates a very strong electrical push. That push forces the electric charge traveling in the spark to the outside of the cage. So as long as I stay on the inside, that charge can't get to me, and I'm going to be perfectly fine. Now relax. I know what you're thinking. You didn't listen to a word that I just said, and you're thinking, I'm about to watch this Jeff die. But you're not, because when I said that electric charge is going to stay on the outside, I meant it. So as long as I stay on the inside, I actually don't have anything to worry about. Even if I put my finger right on this metal point. Now remember what we said about pointing objects earlier. Much more likely to be struck by lightning. Check this out. Bare hand, bare metal. And as long as you stay on the inside of the car, you're going to be safe for exactly the same reason. Now, a couple things to keep in mind. Thing one, lightning can and does strike things more than once. So how much would it stink to have your car get struck by lightning, you to jump out of the car, scream, I'm alive, and then get struck by lightning? You laugh, it's happened. Thing two, the thing that you're in has to be metal. If it's not metal, it's not going to work. If you're in like a canoe, it's not going to work. If you're in a convertible, it's like sticking your head through the bars of the birdcage. You've got to be surrounded by metal on the top, on the side, and on the bottom. And finally, and perhaps most importantly, we're talking about lightning. We're not talking about power lines. If you ever see a power line down to the ground, never, ever, ever try to drive over it. If the power line ever falls on your car, sit there, don't try to drive and wait for the fire department. At this point, whoops. Hold on a second. I didn't think I had that set up that quickly. At this point, I'd like to invite everybody to sit back, to relax if you can. I'm going to play some music with the Tesla coil, and we're going to make a giant indoor thunderstorm, which is what I promised you at the beginning. Sound like a plan?
Yeah.
All right. If anybody has any questions, comments, any good stories, feel free to come and chat with me. At this point, let's sit back and make that thunderstorm. So I'm going to turn that back on. I don't think that music is going to come back on because that's actually not what I wanted to play. You guys ready?
Yeah.
Are you sure? All right. Again, if you have any questions or comments or any stories, feel free to come chat with me. Here you go. Try one more thing. you think it's going to do. But I think we're in good shape. You guys ready this time for sure? All right. No more fooling around. Here we go.
Well, it's all about the same time.
Yeah.